So to begin with, I wanted to thank all of you who survived the lunch, and I hope that you have enough coffee in you to survive to the end of this talk, because this thing is not supposed to be easy. If it was, it wouldn't be re-implemented from scratch every 3 years or so. So what we will be talking about is collaborative text editing. So I think that you probably know from Google Docs and Etherpad, maybe other tools that you are working with. And OK, so beginning, introduction. My name is Bartosz Sypytkowski. Those are my Twitter handles, my blog post, and my email if you want to contact me afterwards. And yeah, what is the agenda for this talk? First, we describe the problem because we will be solving a very specific concrete problem. Then we'll move to two possible solutions for it. And only will briefly mention about operational transformations because they are most well known exactly from the Google Docs, Apache Wave, and stuff like that. And later on, we will move to actual meat of this talk, which is about conflict-free replicated data types, why we could choose them instead of operational transformations, and so on. And also, how we can implement them, how this algorithm works, what problems does it introduce, and actually how can we solve the problems that it does introduce. So the simple problem behind collaborative text editing, we have a document that we want to share with other people. And the case is that we want to be able to concurrently edit this document at the same time. It can be text document, but it also could be, for example, a Git file. However, unlike the Git repository, we would like for our conflicts to be resolved automatically every time and always in the consistent state at the end, eventually. So what would be the problem here? This is an example. So our document is actually one word, continuous. You probably see that it's misspelled here. Alice also saw that. So what Alice did is that she decided to fix it. So she presses the K with the cursor on the correct side. This way, she will introduce a new kind of operation, which is inserting a letter U. I hope you can see that. Does anyone have problems? OK. So she is inserting a letter U at the position 5. This is the standard for this kind of algorithm. At the same time, Bob wants to insert a question mark at the end of this word. And they are first making those changes locally on their own replicas. Everything went fine. However, at some point in time, they need to replicate those operations to one another. So we'll start with Alice. Her operation is replicated to Bob's computer. And we end up with fairly consistent state. However, when the Bob wants to replicate his operation to Alice, we end up with different state. The state of replicas differs, and therefore our document is corrupted. Why? Because since Bob committed his operations, the actual index of the data that we wanted to use to insert our new character has changed. And this is the the golden issue that we want to solve. There are multiple different problems, if we want to go into the details, but this is something that we can start with. So, yeah, nobody is actually happy about the situation. So what could we do? If we are paid for hour, we could just, file the issue with some bug and go home, hoping that the next day this bug will be expected to be solved by another person in our team. But in other ways, we probably don't want to work like that, and we want to actually solve this problem. And of course, when it comes to the synchronization problems, the simple question would be, why not just to use a single central database? And this is something that probably all of us experience at some point in their career. Like, we are producing a simple web application or desktop applications that are connected to some remote central database, probably via some ORM like Hibernate, Entity Framework, or something like that. And everything works fine, but not in this case. One problem is that a single contributor can issue hundreds of operations per minute because, every key press is basically a new operation. So while it's even possible to actually share a single document this way, we probably want to have a system that can, introduce multiple documents to the dozens of thousands of people or millions of people at the same time. Another problem is that when we are replicating operations against the remote database and we are waiting for the confirmation, before we want to show this effect to ourselves or our users, we have some lag. It's inherent thing of sending packages over the network. And this kind of delays are not really something that we can afford when doing key presses, because when we are pressing keys, we want our text to appear instantly, unless we operate on Visual Studio because it's a subject to change there. So another thing is that if we are collaborating on the same text, on the same document, we probably want to do that no matter where we are. So for example, we should be able to continue editing our document in something like offline mode when we are traveling in the train, somewhere in the mountains where the Wi-Fi is just not there and won't be probably there anytime soon. But we still want to be able to edit that document. We don't want it to be frozen until we get online again. And since this implies that we already need to push some kind of conflict resolution logic to our clients, it would be a nice to have if we could actually reduce the cost of having multiple servers for decentralized server-client communications in favor of peer-to-peer communication. So, this way we could scale our applications better because every potential consumer of our application also adds a new machine, new resources that we can utilize this way. So why not push our costs into our clients? It's a nice business model, So the first proposition is operational transformation. And as I said, Google Docs are the most common and famous example of this. Apache Wave is another one. Etherpad is another one. There are plenty of those examples in the wild. So how does it look like? Given the previous example, Alice and Bob are actually making the commits. This is a specific thing for operational transformations, that they are also using their own IDs. In case of Alice, it's A. In case of Bob, it's B. To send those operations over the network. When they apply those changes locally, they also remember something that is, we could call it a transformation. So we say any concurrent update that will come to us after our own, if its index is after the index in which we presented our operations, we will change the index of that incoming operation, shift it by 1, essentially. To solve this problem of us having those, applying those extra characters into our document. So it's simple. When Bob actually replicates his own operation into Alice's replica, he sees that there is a transformations that should be applied to his operation. So we apply that operation and we finish it in the correct state. And on the other side, when Alice wants to apply her operation, she sees that her index of her operation is actually before Bob's, so there is no need for transformation to be applied. And we still end up in correct state. And this is, in very simple words, how the operational transformations work. And yeah, the only problem is that in practice, this is not so easy to actually solve. And Joseph Gentle is one of the people behind Google Wave, which later became Apache Wave. He's also an author of Share.js, which is a JavaScript library implementing operational transformations. And he had a very nice long comment, whole paragraph on Hacker News when he is describing what the problems those operational transformations introduce. And since I don't want to force you to read the entire paragraph, the wall of text on the single slide, I've decided to just insert here a point of this talk. So OT sucks. It's the actual conclusion of his talk. So we will use a different approach. There are different category of data structures that could be used for actually solving this problem. And they commonly known as config replicated data types. In this case, we will cover a single scenario, which is known as replicated growable array, if you are interested in looking for it in the internet. And the basic concept that it introduces is that we had the problem with inserting elements because indexes describing the positions of letters in our document were changing over time as we were adding new characters, So what if we could make them immutable? What if you could create a logical index that describes position absolutely? I mean, once we will assign this character its own position in the document, it stays there forever. Then inserting after, on the right side of target operations would be very easy. And we can do it simply by having, something like sequence number on the left, and on the right, it's something that allows us to recognize which replica actually committed this operation. So now we can see that we have changed a little bit our document. I mean, we've added a special position for each character. And when Alice and Bob want to apply the insert operations, insert in this context means not insert in that position, but on the right side of this position. So insert 6a means find a position in document marked as 6a and add a new character on the right side of it. So Alice wants to add her U letter on the 6a on the right side of the 6a position, and this U character will have its own identifier, which is called 10a. Why 10a? Because the highest sequence number that we have in this document so far is 9a. So we add +1, and we end up with 10a. On the other side, Bob wants to add something new at the end. He adds a question mark, and he's calling this operation he's assigning their position at 10b. Again, the same rule. It's the latest index number that he knew about, sequence number, was 9, so he adds 10, and he adds his own replica identifier. So now it's pretty easy. We apply those operations. We replicate them on the other side. And since the indexes haven't changed, since the characters haven't changed with their position identifiers, because those positions are immutable in context of the characters, they describe the position of the character in absolute way, we can easily resolve these conflicts because we know when we are about to insert our operations. Of course, there is a simple problem. What if both of them wants to insert the characters in the same position without knowing about each other's update? Well, we can make those positions comparable. Like, we first check the sequence number, then we have an arbitrary way to say which replica ID is bigger than the other side. Did this work? So sorry. Okay, so now we change Bob's insert to actually insert another letter in the same position. This part is easy. Now, Bob's is propagating his operations to Alice. We try to insert our character on the right side of 6a. So we need to add extra rule here. Our rule is basically, if we have a character on the right side of the position that we want to place our operations in, which is smaller, which is greater than our own replica ID and our own sequence ID, then we need to skip that character. In case of the Bob, it's actually this rule is not satisfied because it's satisfied, because 10b is greater than 10a, so we can insert his operations in between. However, when we are propagating Alice's operation, we see that her position ID, so 10a, is actually smaller than 10b. So what do? We skip over that operations to the next one. We see now on the letter O, we have position 7a, which is actually smaller than 10a. So it's free place to insert for, the character for us. And this way we can arbitrarily resolve any conflicts that can occur from inserting in the same position in every single case. It's proven. So the problem is about deleting the operations, because we are using those position identifiers. So what if one person wants to insert the operation after the character that was removed by another person? And here is this little problem, because we need to use tombstones. There is actually no other way to solve this problem, at least at the moment. So basically, when we are assigning deletion, we don't actually delete our character from our document, from our data structure. We can remove the content, because we won't need this letter anymore, but we still need to remember the position and where it was in the entire document. This way, we can still resolve our conflicts, of course, at the cost of extra memory used here. Okay, so this was, like basic 3 rules of applying operations on the replicated Grable array. Now we'll come to some more nitty-gritty details about how we could optimize some of those stuff I was talking about a little bit ago. So first thing is how to replicate those operations, because one of the problems is that we need to be sure that we are able to satisfy following rules. One, we need to, the characters we are inserting locally needs to be propagated to remote replicas in the exact same order, because if we are inserting A and then B after A, we must be sure that when we are replicating the stuff over the web to another person, the order of A and B must be preserved, because if we will pass B before A, we won't know after which character we want to place our operations, because A was not there yet. Other thing is that we need to acknowledge, of course, every single of those operations, and we cannot wait for this acknowledgement, because this would introduce lag, and we don't want those delays in our applications. So there is a pretty simple way that we already used to solve that stuff, event sourcing. So we have a distributed event log. However, unlike, for example, event logs in style of Kafka, NAS.io, and things like that, our event log will be actually multi-master event log. So there is no single master that is responsible for propagating, those operations to other replicas. But the relaxations here is that we can introduce something that's called partially ordered log, which means there is no total order of operations. This is the example I've used to, explain you how those algorithms work, written in the event log. As you can see, Bob's operations, the last 2 operations, are in different order. This is because Bob applied his own operations first, and then only after that received operations from Alice. But we already know from the examples before that these operations, even if the logs are not in the same exact order, they will produce the same document eventually. And this is something that we can rely on. And what can we use it for? Well, file formats? No, actually no. Seriously, no. But for example, one of the nice things of that feature would be a history. If we can keep event log, we could, apply undo operations over, characters that we inserted. And if we want to persist that, because we probably should, then we can even do that undo operations when we will, close, shut down and open again our applications. So it's a nice, side effect that we could use that in our applications. So, other problems. One of the problems that we have here was that we have assigned a single position identifier for every single character. And actually, how it actually looks like, basically, we wrap our characters in cells where every cell has its own position identifier and points for the next position that we are interested in, because those stuff are not doesn't have to be specifically inserted into array or string. They are usually implemented in form of something that we are calling ropes. Who of you are familiar with ropes data structures? Yeah. Lunchtime. Yeah. Sorry. And what ropes are used for are actually used for fast string concatenations in real-life scenarios. So if you want to insert a single character, you don't need to reallocate the entire array for entire document that you are interested in. Instead, we have tree-like data structure, but because it's tree-like, it means that we still need to have nodes pointing for the actual positions that we are interested in, and this also adds overhead. Finally, it means that if we want to store those characters each in separate cells, we would pay much higher costs in terms of actual memory used and also persistence of the disk if we want to persist that data structure than actual data that we are interested in. So how can we store blocks of text instead of single characters? And this is something that we could actually do. It's called blockwise replicated GraphQL array. And what we do is basically we add offset that points in the on the index inside the block of characters, and we add it to actual position we are interested in. And how does it look like? So this is another example. This is a single block of text that we added in a single commit operation. We could, for example, imagine that we don't display those characters to end users as we are, inserting them in our, pressing them on our keyboard. Instead, we could, for example, wait for something like half a second or quarter of the second before committing that operations as one block of text to other parties. So here we have something like that, this example, and this is actually also great in another kind of issues. I mean, if you want to insert characters one by one into something like raw data structure, it works great until we want to do something like copy-paste operations. Because imagine if you have to copy-paste like 10,000 characters at once. We would seriously, lag our editor to actually apply those characters one by one. Here, we can apply it as a single block of text. So let's say that we want to insert a new word somewhere in between, inside this block text that we already have. So we basically tell that we want to insert a new block inside this block that we already have that is identified by 1A at the offset 5. So what do we need to do? It's simple. We split the block we have. However, we add a link between new blocks, just to remember that somewhere in the past they were supposed to be a single block of text. Why? Because we need that in the situation when another, you know, like some more people were actually trying to insert something in this place, because we don't know how many people are actually you know, operating on the old version of that single block in the time when we are actually implementing this new operation, this new update. So we are remembering the link between blocks. We are marking the second sub-block with 1a /5, let's say, to mark what was the offset, what offset in the previous block, this new block was supposed to start at. And we just insert our new operation. This is how it works. Deleting the text inside is also very simple. So let's say that now we want to have 3 characters deleted, starting from the position 1 of block 1.8 from the offset 12. So we again split this block into parts. We remember the split links, this is how they are called, between those new created blocks. And we just mark one of those blocks that we are interested in as tombstone. Side note from that is not described in the paper, is that if you want to delete a part of the text that is longer than actual length of the block you are interested in, you need to commit it as a series of delete operations, one per each block. It must fit into the blocks. Because if you want, after, you know, committing the operations on the other side, if you want to delete some text from the block and you have, you know, like 12 characters remaining, we don't know what this remaining part is supposed to be inserted, supposed to be deleted from where, because we don't know what, you know, the original creator of that operations have seen in his time. So this is how we can optimize our RGA or replicated graybars into block operations. So another problem that I've already introduced was about tombstones, because if we are heavily editing some kind of text, it might turn out that we have, like, for example, 5 kilobytes of actual text that we are showing to our users, but underneath it could be like 500 megabytes of data that is necessary to resolve all of the conflicts that we introduce along the way in the history of that document. And it would be nice if you will be able to delete those tombstones as well. So one thing that is worth noticing is that we can insert only, as users, we can insert only operations in the text that we see. We don't see tombstones, so we don't ever, so once we have noticed that we have a tombstone in our text, we will never assign insert operations that is relating to that tombstone. So once we are actually able to tell that every peer editing this document have seen that tombstone, then we will be able to prune it, because, you know, it won't be referenced any longer by anyone, basically. And this is something that we can use in our implementation. So how would this look like? Simply, we could apply timestamps to our tombstones. When we are about to delete, we say, and we send a delete operation in which we say, let's delete this number of characters in this position, and this is the tombstone to say when I have deleted this. And for now, I'm marking them as T1, T2, and you can see it later on. So we are applying that operation. And then we can, you know, in any arbitrary point in time, send another special kind of operations, which is prune with some new timestamp. And this way we say, remove all of the tombstones that have their timestamps lower than the timestamp I've created in this prune operation. And this way, we can, you know, just simply compare the timestamp of each tombstone and remove the ones that are below the threshold that we are no longer interested in. So, what could be those timestamps actually? There's one problem, because as we were saying, those things are supposed to work on the edge devices. So I mean, not like in our data center, more like on every person's computer. And imagine that we could use, in theory, operating system timestamps, the standard clocks. However, what would happen if, for example, somebody is using a free trial of his license and trial has ended? So what do? We move our clock like month back. Of course, nobody ever did that, you know. But this is possible. So yeah, in his case, he will also grant us a corrupted timestamp, so we won't be able to actually use it. And this is something that we could make a separate talk about, but not this time. The key point here is that when we are talking about transactions, operations, and applications, and so on, we are actually interested in order of the operations. It doesn't have to be a specific point in time. It has to be something that we can compare to. This is what we are interested in. So the simplest way to do comparison is to do sequencers, like in databases when we are creating a new ID for our column, primary, auto increment, something. So our database is adding monotonically increasing numbers. However, as we said, it's not applicable here because to actually implement incrementing only timestamp, our replicas would have to actually communicate with each other to determine what the next value of the timestamp should be. So another, higher type from that is called dots, when we basically have something that we already presented in those absolute positions. So we have monotonically incrementing operations, but also we apply replica IDs to them. So every single replica has its own sequencer and can, forward with those and send them in pairs. What we can do onward from that point is that we can use vector clocks. Who is not familiar with vector clocks? It was supposed to be a tricky question, because if you are too lazy to actually raise your hand, then you will make my job easier, but not this time, sorry. So yeah, vector clocks are, in their essence, something that we can use to compare time based on the dots produced by every single replica, but we group that dots together per every replica ID. So if A has committed, the operations, they are incrementing their sequence number, but also applying their replica ID. Then if B have also the same thing, we can combine those information together into a single structure. It's like a map from replica ID to sequence number, and we can use it later to comparison or to version our documents, actually, because this is what we are interested in. Our document can be versioned by those vector clocks. Each vector clock describes a new version of our document. And how does it look like? How does it work? We can actually order our vector clocks, but not only order them using less than, greater than, or equal constraints, but also detect the concurrency of operations. And how do we compare them actually? So what we are doing basically is we are comparing the corresponding replica IDs on each of the sites, and we are comparing the numbers. If all of the numbers are the same, then those vector clocks are equal. If some of the numbers are greater than or equal, then we can say that the vector clock, for example, in this case on the left, is greater than the one on the right. If all of the corresponding entries are less or equal than, then entire clock is less than this counterpart. And when we have mix of less and greater, it means that we've detected a concurrent operation. because basically one part, one replica have assigned some operations. In the same time, another replica assigned its own operation, but without knowing about each other. This is how we can detect concurrent updates. And this is often used in the distributed databases, in distributed systems, to detect concurrency problems and to resolve them. And you probably could ask, what if one vector clock doesn't have corresponding replica? Because this could happen. Then we simply treat this as a 0, default value. Now, yeah, how do we want to resolve our concurrency updates? Quite often in optimistic concurrency, according to optimistic concurrency rules like last write wins, we are checking for the timestamp and the conflicting operation with the higher timestamp usually wins. Of course, with last write wins, it's a problem because we are usually dropping the operation that has lost in this conflict update because it has lower timestamp. But in case of vector clocks, it's not really a problem, because applying a max to vector clocks is basically taking the corresponding sequence number of the corresponding replicas and picking the max operations of them. Why? Because every single update is ever incrementing. So we know that the biggest value is the most actual one. It's most up to date. So now we have vector clocks. The last thing that we need, okay, first, with dots, we can track our own order of our own operations. With vector clocks, we can track orders of operations assigned by other people to us, as well as our own. But what we need to actually have here is something that will tell us what every of the peers saw from every other peer perspective. Because if I will be able to tell that all of the people have seen that thing, if all of the people have seen what everyone others have applied to them, whatever operations have they received, then every single one of us will be able to tell what is the minimum timestamp that we all have seen without communicating with each other, without actual synchronization, locking, and stuff like that. And this is solved by dots, vector clocks, and now matrix clocks. So matrix clock is basically a list of vector clocks when we are tracking a vector clocks of every single other user. Now, how to determine a seen by all event? It's simple. We pick the rows representing vector clocks, and we apply min operation. Like we have max when resolving conflicting updates, here we are applying min. So we are taking minimum values of the corresponding replicas. And this gives us another vector clock. And what does this vector clock mean? It's basically our pruning point. Now we can rest assured that every single document that was submitted here has seen all of the tombstones that are less than or equal than this vector clock. So now we can replace our magic t variable with those vector clocks. So let's say that we assigned tombstones in forms of timestamp to tombstones in form of those vector clocks, and we want to make a prune operation. So we are checking against our prune timestamp for every single tombstone timestamp that is less than the value that we are interested in. If it's bigger, if it's greater, or if it's concurrent, it means that, sorry, but we cannot guarantee that another person is not using this actual block of text on their side to perform some updates. So we need to actually keep it in memory. And of course, this goes with the problem. What if somebody started to editing his or her document decided that he needs to go for the cigarettes and didn't show up for the next half of a year. We cannot, delete any data here because we still need to check, because he still could possibly edit his version of the document without giving us any acknowledgement about that. So yeah, this is kind of a problem here. But I think that this is something that actually is not possible to resolve automatically. It's something like more user intervention, something like, let's make the owner of the document, for example, kick out that person from our document. So, when he go back online again, then he needs to just, copy paste his changes manually, because I don't think that there is something, a way to solve that without user intervention. If you don't know something, you cannot assume that you know it. So yeah, this is basically what I have right now. Here are the references. The reference to the Hacker News, full Hacker News talk related to those operational transformations. There's also conflict-free replicated data types about JSON data type, which was introduced by Martin Klefman. If you are familiar with designing data-intensive applications, it's his book, and he actually proposed a library in JavaScript which is called AutoMerge, which allows you to build a conflict-free replicated JSONs in JavaScript. And I think it's great, actually. Link to raw data structure and link to the official paper about this blockwise replicated grammable arrays. And the last one, it's my GitHub repository when I'm playing with various implementations of CRDTs, including blockwise replicated data arrays in F#. So, thanks.
Okay. Let's thank the speaker. We have time for, I think, 1 or 2 short questions. So, are there any questions? Okay. One question.
So thank you for your talk. It's very interesting. Well, there are many questions from the distributed system side, but I will do only one. Does your solution scale?
Yeah, it can be web scale. Of course, you don't need.
How big will be the text?
For that.
Yeah,
it's possible to do. I haven't got a production-ready implementation right now that I can show you. There are several applications out there that are using various replicated data types, conflict-free replicated data types, sorry. I think that there's even one editor, it was called Conclave or something like that. It's written in JavaScript, has open source code, and it's using CRDTs to actually allow you the collaborative text editing capabilities.
Oh, there is one more question.
Okay, thank you for the talk. The question is, I couldn't help but notice that the blockwise Go replicate arrays, and when the text is edited intensely, the blocks get splitted eventually into like single characters, up to single characters. So at some point you may need a merge step or something like that. What's the approach in there, like going further in there?
Yeah, I am aware that there is such possibility that eventually our blocks will be split into blocks of single characters. It is possible, unfortunately. I don't have any, like merge operations for them because it was not my invention, I would say. I just read the paper and implemented what the paper said and, played around that. So I cannot answer for this question. But, in practice, I would say that it's fairly uncommon to have something like, splitting block of text that can be possibly like 3,000 words into a single character units. it's
So basically,
very edge.
maybe there is we could safely merge them into blocks, back into blocks while pruning them, maybe.
It would probably need a separate kind of operation, but as I say, I cannot.
Yeah, I get it. Not
You know,
quite
it's
realistic.
not something that I am able to figure out from the thin air right now. Sorry.
No, that's okay. Thanks.
Okay, so let's thank the speaker once again.
Thanks.